Presentation entitled Respect the Chemistry. It says Respect the Chemistry by Walter White. Okay, the learning goals for this particular presentation are classify a substance as an element, a molecule, or a compound, and be able to identify the chemical properties for various substances. So here's what we already know. From middle school, we know that the digestion of food breaks into larger particles into smaller parts. We know that chemical properties are related to valence electron structure from earlier grades, and we also know that the physical properties can be examined independent of other substances. Okay, so now here's what we learned in the lab. We learned that chemical properties determine if a chemical reaction will occur. So what happens? Does it, for example, react? If it reacts and makes something boom or a flammable if it burns, that's an example of a chemical property. Chemical properties depend on the type and the arrangement of the atoms. So, we have elements, molecules, and compounds. Chemists classify the reactants and products, okay, that's what happens before and after a chemical reaction, as elements, molecules, or compounds. An element is classified as a substance that consists of a single atom of a single type. So, in other words, you have a single atom of, let's say, iron. Okay, that iron exists all by itself. Now it can be next to another iron, but they're not connected in any sort of way. You have two irons that are close to one another, but this would be elemental iron. Okay, elements can be found on the periodic table. So if you were to look at the periodic table, everything on here is considered to be an element. So it exists as an atom by itself. Okay, it's not an example of Avatar, Earth, Wind, Fire, Air, and all that kind of stuff. Molecules consists of two or more of the same atom joined together in a chemical bond. An example of this would be if you have an oxygen combined with an oxygen. Okay, so we'll call them O and O. Instead of these things acting independently like we saw in the iron, they connect to each other. When they connect to each other, they are no longer individual atoms of oxygen. Instead, it represents an oxygen molecule because it's two or more of the same atom joined together in a chemical bond. This is not an example of a molecule. The reason why is it consists of two different atoms. You have the white atom, which is generally referred to as a hydrogen, and you have the black atom, which is generally referred to as a carbon. Because you have two different types of atoms, it's no longer going to be a molecule. Instead, we call it a compound. A compound consists of substances with one or more type of atoms, including ones that are different. So here's the kind of interesting thing. You have this is classified as a compound, yes, and this is classified as a compound. I thought you said, well, wait a second. You said that this was a molecule. And it is. It falls under both classifications. So you can say that this is a compound or a molecule based on what it is. So element is something by itself. Molecule, two or more of the same things. Compound, two or more of anything. So it comes down to the whole idea all thumbs are fingers, but not all fingers are thumbs. Okay, all molecules are compounds, but not all compounds are molecules. So this right here is a very, very narrow definition compared to this. So all molecules are compounds, but not all compounds are molecules. So if someone gives you the name of a substance, where can you look to see if it is an element? Remember, everywhere if we want to see something as an element, we look at the periodic table. If I give you something like methane, and I say, hey, tell me if methane is an element, you would look on the periodic table and say, is methane on the periodic table? If the answer is no, then it's not an element. If the answer is yes, then it is an element, and the answer is, of course, methane is not on the periodic table. Next it says determine which of the following substance below is an element. So I'm going to use the knowledge of trying to say, is it on the periodic table? The first thing I do is I look for brass. Brass is not on the periodic table. Sometimes people look at Br and go, oh, Br, that must stand for brass. No, that actually stands for bromine. You need to use a periodic table that has the names of the elements as well. So brass is not on the periodic table. Next is carbon monoxide. And people stop and they go, oh yes, carbon is on the periodic table, it's C. And that's true, but that's carbon by itself. Whenever you have carbon by itself, carbon is an element. But whenever you make it carbon monoxide, it is not an element. Next, you have potassium sulfate. Potassium sulfate has two things, so because of that, it cannot be an element. The last one is zirconium. Zirconium is famous because a lot of times it's used for fake or imitation diamonds. Zirconium is on the periodic table. It's Zr, and therefore it is an element. So the only one that is an element is zirconium. Next, it says classify the substances below as a compound, element, or molecule. The first thing you can do is you can say, okay, both of these things fall under the compound, okay, because they both have more than one element. Now, that compound definition is the best definition that I can have for this one because it has two different substances. It has something that's like a nitrogen. You're not supposed to know that blue's nitrogen. And then the hydrogens. So because of that, you can say, okay, this thing right here represents a compound. But then you look at the other one and you say, yes, this is a compound because it has more than one atom, but it has a more specific definition of being a molecule. And the reason why it's a molecule is because all of the atoms are the same. Since all the atoms are the same, it has to be a molecule as well as a compound. Next, we say quantitative and qualitative analysis are both useful in chemistry. Are chemical properties more likely to fall under qualitative or quantitative? And that's going to be qualitative because it determines on how many there are, or doesn't depend on how many there are to see if it's going to react. A chemical property is a characteristic describing how a substance will interact with another one. It cannot be measured independently. So I can't say, oh, this red substance right here is very reactive. The reason why is I need something to react it with. So I can't measure the chemical property of the reactivity of this red powder without having some sort of other substance to react it with. So examples of chemical properties include rust or tarnish, which is generally called oxidation. So it's the interaction of a metal with oxygen, usually air, to form a new substance. So you see an example here where iron is mixed with oxygen to form iron oxide. Okay, you can see it for iron, for rust, for copper. Those metals generally oxidize and they rust/tarnish. Neutralization is when an acid mixes with a base to form salt in a water. Okay, once again, you see how it's something mixing with something else. It's an example of a chemical property. How does an acid react whenever it is mixed with a base? Next, you see reactivity with water. This is an example of you can take something like sodium and you can actually put it in water and it will burn because it's reacting so explosively. So some substances will react with water explosively, and that's reactivity with water. Once again, you're saying, how does it react when I put it with this? Not just what is it by itself. Another chemical property is toxicity. And toxicity is, can something do damage to an organism? Now, the damage is generally done by that substance reacting in the body. So toxicity is generally considered to be a chemical property because it's reacting with something in the body. Now, just so you know, everything is toxic at some level, even water. And you see an example of this is the woman loses sight after drinking too much water. There's also examples of people dying from something called water toxicity. So every substance that you consume is going to be toxic at some level. Now, there are some things like lead, which are toxic at very, very small levels, and there are things like water, which are toxic only whenever you consume a vast, vast amount. So they have different levels of toxicity, but you have to be careful what you consume, regardless of, oh, it's just water, or oh, it's just this. Next, we have flammability. That's what we observed in the lab. It's the ability of a substance to combust or ignite, and it's generally measured using a standardized fire test. An example of a flammability says if you've got water and ethanol, both of them are clear liquids. Okay, but you can distinguish between them because ethanol will burn. If you were to put a match to ethanol, it will light into a blue flame, whereas water will not. Water will just put the flame out. So flammability is one of the ways that you can tell the difference between different clear substances. And the next one is called degradation. And degradation is the process by which a chemical decomposes or breaks into smaller pieces. So a lot of times our clothes tend to be made out of large things like these polymers. But what happens is these polymers are kind of unstable in the sense that when you wear them, just by normal wear and tear, it will break these molecules, and it makes the fabric or the clothes that are made of that particular fabric kind of wear out, even though you didn't put a hole in it or anything like that. It just kind of wears out on its own. That's the degradation, because you have some very, 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 very large molecules, and they just tend to break down naturally into smaller molecules because it's more stable that way. That's the example of something called degradation, because it's a substance that is reacting with its environment to break into smaller pieces. Next, you have pH. pH is a measure of the acidity or basicity of a substance. So, is it an acid or is it a base? An example of this is if you were to look at lemons, lemons are highly acidic. So, they tend to be like a 1 or a 2 on the pH scale, which means they're very, very much an acid. Okay, whereas you have something like ammonia or bleach tends to be very basic, which means how much does it react with water to form either H pluses or OH minuses. Okay, H pluses are associated with acid. Okay, OH minuses are associated with bases. But once again, it's the idea of this substance reacting with water to make one of these two. So fundamental B1, it says determine property in terms of chemistry. We talked about this in the previous example. Remember, property refers to a characteristic. Okay, that's all property means. Now, if it's talking about a physical characteristic or a chemical characteristic, that's where our definition has to change. Next, it says list 3 chemical properties involved in digestion. So you may not remember this from middle school, but you have acid in your stomach. So one of the things that you have is the acid will break down things in the stomach. So one of the chemical properties is your food's ability to interact with acid. The second one is you have enzymes in your stomach. Okay, and those enzymes have the ability to interact with your food. And then the third one, there's lots of different examples, but if you were to look at the third one, your stomach does have some ability to neutralize basic substances because of its whole idea of its acid. There's lots of different enzymes that are there. You actually have enzymes in your saliva. Your saliva has enzymes in it as well. So there's lots of chemical properties that are involved in digestion because digestion is the breaking down of food. It says forensic evidence is often used in criminal trials. If a person is charged with attempting to poison someone, would it be necessary to prove your case with chemical or physical properties? This is kind of a tricky one because it kind of depends on what you're looking at. Generally speaking, you can use chemical properties to help you identify what it is. But you can also use physical as long as they're intensive properties. Okay, something like boiling point. The problem with using chemical properties is you destroy your evidence. Okay, because the whole process of a chemical property is you're reacting it with something to change it into something else. So generally speaking, you'd want to use physical properties. Finally, it says physical properties were divided into extensive and intensive properties. Can the same be done for chemical properties? And the answer is no. And the reason why not is because chemical properties are measure an ability, a substance's ability to react. So if I have a single atom of something, it should be able to react with something, regardless of whether there's 2 or whether there's 500 million of them. All chemical properties are considered to be intensive, and so we don't even label them that. Okay, all chemical properties are just intensive. There is no extensive chemical properties. Examples is scientists discovered that a potassium-doped Buckminster fullerene, otherwise known as a buckyball, a buckyball, which is this kind of interesting structure right here, becomes superconducting at 18 Kelvin. Describe the chemical and physical properties in this narrative. Well, the first thing you need to realize is we're only looking at physical properties. And what that means is I want to describe the characteristics of this particular structure only on its own. So really, when I look at it on its own, the only thing that I can really say about this thing is this right here is the structure. Okay, that's the structure of it. And then it's at 18 Kelvin, that's a temperature. I can't say it's really superconducting because that's how it reacts with potassium. So when you have potassium and Buckminster fullerene together, that's an example of what we call a chemical property because it's how it reacts with something else. Okay, next, we need to differentiate between what's called an extensive and an intensive property. An extensive property is one that changes when the amount of substance changes. So if I have a small amount of stuff and a big amount of stuff, I get different measurements. Okay, so an example of that would be height. weight, mass, all those things are examples of extensive properties because what they do is they change when I change the amount of material. So examples of extensive properties include length, mass, area, volume, weight. There's lots of different examples. So the way that you test to see if it's an extensive property is you say, I take a small amount and I measure, and then I take a large amount and I measure. If you get the same value, it is not an extensive property. If you do get the same value, then it's an extensive property. So we contrast extensive properties with intensive properties. Intensive properties are ones that do not change depending on the amount of material present. So you take a small amount, you take a large amount, you take measurements of both, and whenever you take measurements of both, it ends up being the same. Okay, an example of an intensive property is the boiling point of water. If you have a very, very, very small cup of water, it will boil at 100 degrees Celsius. If you have a huge vat of water, let's say the ocean will still boil at 100 degrees Celsius. It doesn't matter what the size of the amount of material is, it just depends on what the material is. Not how much, just what it is. So that's an example of an intensive property. Other examples of intensive properties include specific heat capacity, malleability, color, reactivity, conductivity. Those are all examples of what we call intensive properties because they do not depend on how much material is present. So you can generally organize matter on a classification scheme. You can divide things into physical properties and chemical properties. We'll talk about chemical properties in the next presentation. But once you're a physical property, we can further subdivide into what are called extensive and intensive properties. So make sure that you understand that once something's defined as physical, it can be a physical intensive property or a physical extensive property. So define the terms below. The first one is a physical property, and that is a characteristic that can be measured. You can measure independent of other things. Okay. For an intensive property, it is one that does not depend on the amount of material, on the sample size, we'll call it. And we'll change color so we can see it a little better. It does not depend on the sample size. Okay, an extensive property does depend on the sample size. Next, it says which of the following properties can be described as an extensive property. Now remember, the definition of an extensive property is one that changes based on sample size. Okay, so remember, anytime we see a triangle, it means change. So if you were to look at here, it says volume. Does the volume change as the size of the sample changes? And yes, it does. Does the density change as the sample size changes? And that's no. Okay, it doesn't matter if you have a small amount of water or a large amount of water, the density is going to be the same. The mass does change. The boiling point does not change, and the reactivity does not change. So the two things that we have in this case are going to be mass and volume. Next, it says which of the following properties would be best in determining the identity of an unknown substance. So if I want to know what it is boiling point going to be helpful in identifying what it is? Okay, I think so. I don't think the mass would work. I don't think the weight would work. I don't think the length would work, and I don't think the volume would work. The reason why is these are all extensive properties. Okay, they will change based on how much is there. But the boiling point remains the same. If you have 5 clear liquids and one of them boils at 100 degrees Celsius, well, guess what? That one is water. If it doesn't boil at 100 degrees Celsius, well, then it's not water. It could be something different. So intensive properties are useful whenever you're trying to identify an unknown. Okay, it says a forensic pathologist obtains a sample of an unknown chemical taken from the home of a murder suspect. The sample, initially 100 mils, spills as it's being transferred, leaving only 5 mils left. What property can be analyzed by the pathologist and hold up on cross-examination? So if you were to look at this, they changed the sample size. Okay, I went from 100 mils to 5 mils. The change in the sample size indicates that the only thing that would work would be intensive properties. Okay, all extensive properties is saying, hey, there's too much of this in this sample, are no longer valid because you've changed the sample size. But intensive properties, as far as identifying what it is or saying it boils at this temperature, those are still valid. Finally, we need to talk about density. Density, objects can be referred to by the ratio of mass to volume. The density is constant for all homogeneous objects, and what a homogeneous object is it's the same everywhere. So if you were to take an example of orange juice. Orange juice is not considered to be homogeneous because you have pulp on the bottom and it's kind of watery at the top. So if I were to take a sample here and a sample here, I would get different substances based on where I take my sample. So that is not an example of something being homogeneous. However, if you were to look at something like milk, milk is generally considered to be homogeneous because if you take a gallon of milk and you take a sample here, it's going to be the same as a sample here. Well, if something is homogeneous, then it has a constant density throughout. So the ratio of mass to volume is always the same. The density calculation uses this formula right here, where density, which is right there, density is equal to mass over volume. Now, we talked about in the physics part of this class that mass is generally referred to in kilograms. Well, in the chemistry part, a kilogram is really a large amount of mass. So we tend to see grams for the mass, even though it's not the standard unit. The standard unit is still the kilogram, and you see that here. These are the standard units. But in chemistry, we tend to see grams per centimeter. Okay, so even though the standard unit for volume is the meter cubed, you tend to see the centimeter cubed instead. And those are those chemistry exceptions. So most of the time you will see mass in grams, and you will see volume in either milliliters or centimeters cubed, which are the same thing. 1 milliliter cubed is the same thing as 1 centimeter cubed. So let's look at some examples. It says, rank the substances below from the least to the greatest density. So what you see right here is called a density column. And in the density column, you can look at and you can say, okay, what is the most dense and least dense substance? Well, the more dense a substance is, the more it will proceed to go down to the bottom. Okay, things with less density will float. Okay, that's why air floats on top of water. Okay, because it's less dense than water, so it rises to the top. So what you see here is we can clearly say that vegetable oil is going to be the least dense. And then we can clearly say that honey is going to be the most dense. So we can go in order. It goes vegetable oil, water, dish soap, corn syrup, honey, as far as the density from least to greatest based on where it separates out. Next it says, what is the density of colored water if a 100 gram sample occupies 100 milliliters of volume? So I need to use density equals mass divided by volume. Okay, and when you do this, the equation that we're going to use is density equals mass over volume. Okay, whenever you plug your numbers in, remember we have to write our given in our equation. The next thing we need to do is we need to plug it in. We'd say density is equal to 100 divided by 101, which is pretty close to 1, but the answer is actually going to be like 0.9999 grams per milliliter. Now, the density of water is generally considered to be 1. It does change a little bit with the temperature, but from now on, every time we talk about the density of water, refer to it as 1 gram per mil. Next, it says you place a solid piece of iron into a specifically designed beaker. The beaker is then put over an intense flame. Describe the density of the metal as the heat is continually added to the iron. So I've got an iron sample, and then I'm going to add heat to it. Now, you've seen something similar to this if you've ever taken a balloon and heated up a balloon. Okay, or have seen a hot air balloon. When you add heat to the balloon, what happens to the volume here? Well, the volume of the balloon expands outward. Okay, and the same thing happens whenever you talk about iron. If you add heat to iron, it expands outward. Okay, a hot iron is going to occupy more volume. So we say the volume increases as you add the heat. So now it says to look at the density. If you look at this, we say density is equal to mass over volume. Well, the mass of the iron doesn't change. You're not adding more atoms of iron. But what does change is the volume. And remember, volume is on the denominator. So if you're taking this and you're dividing by a larger number, let's say the mass was 10. If the mass was 10 and the volume was originally 2, okay, that's a certain density. But since I increased the volume, say from 2 to 4, what I've done is I've decreased my density. Okay, you've decreased your density because the mass remained the same, but the volume increased. And that's what happens when you undergo what's called a phase change. And we'll get into a little bit more about phase changes later. Finally, it says the following data is taken from the lab. You have this information right here. It says what is the density of the unknown object. So remember, density is equal to mass over volume. The difference is I don't actually have a volume in this particular case. What I have is I have height, diameter, and mass. Well, mass is going to be really useful. Okay, 520 grams. But the problem is that I don't have the volume. What I can do though is recognize that this is a cylinder. So from math class, you would say that the volume of a cylinder is equal to pi r squared h. Okay, you look at this and say, okay, well I've got h, and I've got the diameter. If I divide that by 2, that's the radius. So now I've got 6.1 is the radius, and I can now plug in. At this point, you would plug in and you would say the volume is equal to pi times 6.1 squared times 20.05. That would now give you your volume. Since this is a mastery level question, you should be able to take the mass and the volume and plug it in and solve for the density.